All right, chapter 20 is getting into ketones and aldehydes. We've got a whole chapter dedicated to the combo of ketones and aldehydes. But before we get too far into this chapter, I wanted to go over a little bit of nomenclature. We've seen some nomenclature with ketones and aldehydes, so we know like benzaldehyde and basic simple aldehydes. But when we get into aliphatic aldehydes, the rules change a little bit. So let's go over aldehydes first, and then we'll do ketones next. And I'm just going to do a really simple aldehyde first. If we look at this aldehyde, what do you think the first thing we look at when we're trying to name it? Parent chain, right? So in this case, what would our parent chain be? Would it be 5 or 6? 6. You include every single carbon in the parent chain that has the aldehyde in it. And specifically what you do is you start numbering at the aldehyde carbon and you go 1, 2, 3, 4, 5, 6. The aldehyde is always assumed to be at position 1. You can't have an internal aldehyde because that would make it a ketone. And then when you go to name it, this would just be hexane for the 6-carbon chain. And then al would be its suffix. So anytime you see the suffix al, this is the suffix for aldehydes. Make sure when you are identifying the longest chain that the longest chain does include the aldehyde. It must, by definition, include the aldehyde. Let's do a quick example one. And I want you guys to help me name this. So we've got this simple aldehyde down below. Yep.
So when we name aldehydes, since they have to be on the end of the chain, are we just assuming the locus is 1?
Yes, exactly. When you're numbering the aldehyde chain, the aldehyde carbon will always be position 1 in terms of numbering. At least for right now. I'll show you guys a little bit more later. Yep.
Would it be 4-methyl?
Yeah, let's take a look at this one. So we know carbon 1 is going to be the carbonyl carbon. Then we go 2, 3, 4, 5. We know we've got a methyl group here. We know we've got a bromo group here. And then what's the stereocenter? Is that R or S? Oh man, you guys forgot stereochemistry. R. Bromine's going to be position 1, the isopropyl group to the left will be 2, and then the aldehyde over to the right will be 3. So this will be R. So if we try to piece this together, we know that it's going to be R, 3 bromo, 4 methyl, pentanal. So make sure when you name these that you number them appropriately and don't neglect stereochemistry. Stereochemistry is still important. Let's do some nomenclature with ketones too really quick. Let's do a simple ketone first. I'll do this as our simple ketone. The rules are pretty similar. You still want to identify your longest parent chain that includes the ketone in there. So we've got 1, 2, 3, 4, 5. So this would be a pentane. And do you think we want a number going left to right or right to left? Right to left. You want the ketone, just like with alcohols, to be at the lowest position. So you want it to go 1, 2, 3, 4, 5. For aldehydes, the carbon will be position 1. With ketones, they can be internal, so they don't have to be position 1. In fact, they can't be position 1. So if we look at this, we've got a carbonyl coming off of position 2. So what we do is we call this 2-pentanone. So in this case, the suffix for ketones will always be -one. And then the 2 indicates the CO bond position. It's pretty straightforward. An alternate name that people will sometimes use for this will be methylpropyl ketone. So they'll just call it an alkyl-alkyl ketone. That's IUPAC allowed for really, really simple ketones. However, I really prefer that you guys use this sort of naming system. It's much more conventional in terms of naming ketones. So you may see it listed in the book as methylpropyl ketone. Let's take a look at some special cases really quick. So I'll do special aldehydes first, and then we'll go into the special ketones. So let's take a look at some special aldehydes that don't really follow the traditional IUPAC naming. Does anybody know what this aldehyde's called? Formaldehyde. Does anybody know what formaldehyde's used in? Yeah, you can use it to preserve biological tissues. It's also used in particle board. So anytime you get particle board or those desks made of that compressed material, there's formaldehyde in there acting as a binding agent. The next aldehyde that doesn't follow IUPAC rules is this one. And what's this called? Yeah, benzaldehyde. So that's not using the traditional numbering system that we've seen. The other one that you will see occasionally is this one. Does anybody know what this would be called? I'll give you a hint. We've got this pretty common functional group coming off here. So that's an acetate functional group, right? So in this case, the prefix is going to be ACET, and this will be acetaldehyde. This one's also a pretty common one. The other one that's kind of the curveball in this situation is this one. And this will be cyclohexane. Nope, carbaldehyde. So occasionally you do see these unusual type naming systems. Yeah, to be perfectly honest, I'm not sure why they use a different naming system for this. I'd have to look it up more. Let's do the same thing with some special ketones. All right, the first ketone we're going to look at, I hope you guys know this one. What's this ketone called? What is it? Acetone, right? So you guys remember how we had this ACET prefix? So this will be the same thing. In this case, this is just acetone. We've got the ONE suffix indicating that it's now a ketone. The next one that we have is one of our benzene derivatives. What's this one called? Acetophenone. Again, we've got that aceto prefix. And a phenone just means that you've got a CO double bond right next to a benzene ring. So phenone, phenyl ring right next to a carbonyl. The last one that's pretty common is this one. What would this be called? Benzophenone. So it's still got that phenone functional group. We've got the benzene or phenyl ring right next to a carbonyl, and then we've got another benzene coming off. So this is just benzophenone. So some people might call this diphenylketone. However, most people will call this benzophenone.
Okay.
Yep. Does that make sense in terms of naming? I'm not going to spend a lot of time on naming, but Sapling will have a lot of practice problems with there, and if you get stuck, try to refer to the book.
So for the acetone, do we have to have all these memorized?
They may show up. They do give you a list of some abbreviations and what they mean, and I can show you guys a little bit about that once we get closer. Yep.
So none of these follow alphabet name rule?
No, these ones, you see how we didn't really number them or include parent names, where these are kind of the offshoots of the IUPAC, but they're IUPAC allowed. I had a few people asking me about priorities where they're like, well, what if we have an aldehyde and an alcohol, or an aldehyde and an alkene? Which one takes priority? And that's a really good question. So I ended up finding this list of priorities from Master Organic Chemistry, which is online. And it ranks things in terms of most important priority to least important priority. The most important priorities are typically going to be your carbonyl CO double bonds. So carboxylic acids have the highest priority, and we'll cover that naming. Ethers after that, or sorry, esters after that. Acid halides or acid chlorides after that. Amides, nitriles, and then aldehydes are actually a little bit higher than ketones. And then below that, we've got alcohols, thiols, amines, alkenes, alkynes, alkanes, ethers, halides, and nitro groups. I know it's not the most intuitive list, but if you ever are stuck with one of these, you can always refer to these. In general, if I'm going to ask you a question, I'm going to ask a relatively simple naming questions. I'm not going to throw a dozen different functional groups on one molecule. A few people will ask, well, what if the functional group's not the highest priority? That's when you have to treat the functional group itself as a substituent. So let's do an example one. Let's do this one as a practice one. What's going to be highest priority? The ketone, right? So the parent's going to have the "-one" suffix, right? So if we look at the suffix, we've got "-one" right here. Sorry, I know this is a little bit small. And then if we look at the alcohol, because it's a substituent, we're going to treat the alcohol as a hydroxy group. So if we go through and we number this, we know that the numbering will likely go 1, 2, 3, 4, and 5, because we want to minimize numbering for our parent chain. So we know this will be a hydroxy. And let's try to name this now. Is this R or S? S. So we could say S2-hydroxy. Whoop. 1-cyclopent, because we've got that 5-membered ring, and -one. Does that make sense? So in this case, the hydroxy group's not treated as a priority. Yep.
Do you have to put the line, or is it kind of implied that your ketone is part of the parent and is going to be a substituent line?
In this case, it would be implied that it's at the 1 position. You could do it either way. Yeah, that's a good question. All right, so let's do a little review with how we can prepare both aldehydes and ketones, because we've seen them already in a few of our chapters. And let's start with aldehydes first. We know that we can prepare aldehydes through oxidation mechanisms. Can we prepare an aldehyde from a secondary alcohol? Can I? Can I oxidize this? Yeah, I can oxidize it, but am I getting an aldehyde? No, I'm getting a ketone. So in this case, we can't use oxidation of secondary alcohols. However, what we can do is we can oxidize primary alcohols. Oop. and we can get to our aldehyde. What's the reagent that we need? PCC. So I'm just going to be as specific as possible, and I'm going to fill in PCC. Oftentimes this is done in dichloromethane as your solvent. And if you're a little bit rusty on this, I'll put down the section number that we covered this in. This was covered in section 1310, so that was last term. So the only way we can prepare an aldehyde through oxidation is with primary alcohols, at least right now. Next one we have is ozonolysis. And if you remember all the way back to chapter 9, we can take an alkene and we can turn this alkene into two equivalents of this aldehyde, assuming those R groups are the same. What reagents do we need? So ozone first, and then for the second part, you typically will use a reductant. DMS, zinc, and HCl is often used. What does DMS stand for? Yeah, dimethyl sulfide. So you can turn that into a disulfide and cleave the ozonide. This was covered in section 9.11, so 911. And then we also covered how to make aldehydes through hydroboration oxidation. Does hydroboration oxidation of an alkene give you an aldehyde?
No.
No, it gives you an alcohol, right? When did we use hydroboration oxidation to get an aldehyde? Alkynes, right? So if you remember back to our chapter 10 material, if we have a terminal alkyne, we can do hydroboration oxidation in order to get our aldehyde. One common mistake people make when they're doing hydroboration oxidation, yeah, they lose a carbon. So remember, if you've got this blue carbon here, that blue carbon's still sticking around, and this green carbon coming off the end is going to be where your carbonyl comes off of. And then the reagents we use for this, do we use borane THF? No. Yeah, why don't we use borane or THF? Exactly. You've got two pi bonds. So in this case, you have to use a really big, bulky borane to prevent multiple additions. And then we have to oxidize it by using hydrogen peroxide and sodium hydroxide. Make sure that you remember your keto-enol tautomerizations for this too. That's going to show up again. And this was in section 10.7. Make sense? A lot of review. All right, let's do preparation of ketones.
Oh, that's it?
Yeah, that's really the only methods we know of for making aldehydes so far. All right, preparation of ketones. We said we can do oxidation and get a ketone. And this time we actually need to use a secondary alcohol. And what reagent do we want to use? Man, you're blowing up over there. Okay, PCC or what else? Chromic acid, Na2Cr2O7, H2SO4, and H2O, or any one of any combination you want to get chromic acid. There's like a dozen listed in various textbooks. Either of these will work. This was done in section 1310, if you want to go back and review it. But will this work with tertiary alcohols?
No.
No, it has to be a secondary alcohol. Ozonolysis can also be used to make ketones. And just like we saw in chapter 9, we can cleave this using ozone and DMS at dimethyl sulfide to give us 2 equivalents of our ketone. So you have to pay attention to the substitution pattern of your ketone. And we covered this in section 911. All right, what if we want to convert an alkyne to a ketone? Acid catalyzed hydration. All right, so let's take a look at an example situation for acid catalyzed hydration. I'm going to use a terminal alkyne. Can I use an internal alkyne? Yeah, typically if we're using an internal alkyne though, what do we have to watch out for? A mixture of products, right? You typically only use an internal alkyne if it's symmetric, meaning your mixture will result in the same products. Otherwise, you want to use a terminal alkyne. And we know we use acid, so we'll do H2, SO4, and water. And what's our catalyst? Yeah, mercury 2 sulfate. And if we do this, just like I said, make sure you keep track of carbon. So we've got this blue carbon and we've got this green carbon. We know this time we're going to get a ketone, and then this green carbon, I'm going to even label it as green, will be dangling off of the end, and you've got this blue carbon right there. So you get the more substituted side of the double bond. We covered this in chapter 10.7. Do we know of any other ways to make ketones? Anybody? Friedel Crafts. Yeah, we just covered one other way. And with Friedel Crafts acylation, we said you can take a benzene or substituted benzene, and you can react this with an acid halide. And I'll just put R on, an aluminum trichloride. And if you do this, you can get a ketone installed. We also saw a variant where this can be used for aldehydes. However, that carbon monoxide HCl mechanism only works under certain circumstances. It's not universally useful.
Is that really making a ketone because you already have one?
Well, we have an acid halide, not a true ketone, as a reagent. So this is kind of a variant of it. If we have a strongly deactivated benzene ring, will this work? No. Remember, Friedel Crafts reactions only work if you've got a ring that's activated or at the very least weakly deactivated. If it's moderately or strongly deactivated, it won't work. All right, so now we get into new chemistry. Enough of the review. Chapter 20 primarily focuses on nucleophilic addition to ketones and aldehydes. And we're going to focus on aldehydes first. And let's just take our generic aldehyde, and I'm going to keep an R group in there. If we think about aldehydes, we've got a resonance structure where we can pull electron density up. And this gives this oxygen a formal negative, or formal positive, and this oxygen a formal negative. We know the hybrid structure has a partial negative on the oxygen and a partial positive on the carbon. So if we throw in a nucleophile, where do you think that nucleophile is going to attack? Yeah, exactly. So we can look at this and we can say this is a good electrophilic center, or a good electrophile. So in this chapter we're going to look at this a lot, and we're going to see how nucleophiles will react at this carbon. One thing to also think about is we're explaining this as a good electrophile due to electronics, but you can also look at this in terms of sterics, right? With aldehydes, that carbon's pretty accessible because you've only got one hydrogen on there. If you compare this to a ketone, do you think a ketone's going to be more or less electrophilic? Less, because it's going to be more sterically blocked. So let's do the same thing with ketones. And we'll just do a quick resonance structure. Whoops. And I'm going to just extend this arrow down here. And then we'll make a note that ketones are typically less electrophilic than aldehydes. And one argument we were making was sterics, that carbon on the ketone is a little bit harder to reach if you're a nucleophile than the carbon on the aldehyde. What's another argument we could make to explain the difference in reactivity? What was that?
Electronics?
Yeah, electronics. If we look at the ketone, we've got two alkyl groups on both sides. We know that alkyl groups tend to stabilize the carbocation that they're next to due to hyperconjugation. So the ketone is actually a little bit more stable than an aldehyde. If it's more stable, that means it's going to be less electrophilic, right? So we can make an argument having to do with sterics and hyperconjugation. This is a good general rule of thumb. Let's take a look at a mechanism where we're treating an aldehyde or a ketone as an electrophile. The first one we're going to look at is under high pH conditions, so under basic conditions. And let's just choose a ketone. It's really similar for the aldehyde. But let's say this is our ketone, and we've got some sort of nucleophile. This nucleophile, we said, can attack in, and then what do you think happens? Yeah, you can't have a Texas carbon, so we'll just kick electrons up. This is actually somewhat reversible, because if we think about our product, if your nucleophile is also a good leaving group, that negative charge on the oxygen could kick down and kick off your nucleophile. So this is typically thought of as an equilibrium, not a true one-way reaction unless the equilibrium really favors the product side. And then in the next reaction, you typically have some sort of proton source. So I'll just do H plus in brackets. And you can protonate your oxygen. Oops. So that's the simplest mechanism for nucleophilic attack under high pH conditions. What was that?
With that, based on what your substituents are, would you get a racemic mixture?
Yeah, that's a good question. If we think about our nucleophile attacking, do you think it'll prefer attacking from the top face or bottom face? It really doesn't matter because it's a trigonal planar compound, and so you will end up as a racemic mixture in the end. There are some tricks you can use to get this enantioselective. However, that's what you would see in an advanced organic chemistry course. Yeah, good question. Let's even put that down, racemic. All right, let's do simple mechanism under low pH conditions now. Oop. All right, let's do a ketone again. Oops. Fastest reaction in chemistry? Acid-base. So before the nucleophile even gets a chance to attack, if it's in acidic conditions, we know acid-base chemistry will be super quick. We'll protonate the oxygen on our ketone. I know this looks funny, but if you think about it, the oxygen, even though it has a positive charge, has something else going on. Resonance, right? So if we think about this, the oxygen doesn't have that much positive character anymore. In fact, the positive character is primarily on the oxygen. And now if you're a nucleophile and you've got some sort of negative charge, like we said, it's going to really favor this electrophilic carbon on the bottom there. So you'll end up with your nucleophile and then your alcohol. Only difference between the two is under acidic conditions you protonate first, under basic conditions you protonate second. So just pay attention to that if you are doing a mechanism. You always have to ask yourself, am I under acidic control or basic control?
Is there a chance for the nucleophile to attack the oxygen?
That's a good question. If we tried to do a bond to that oxygen, we'd be violating the octet rule. So it's just not going to happen. Yeah. So again, you're going to end up with a racemic mixture of products out of this. All right, let's make a couple of reaction notes. The first note that I always want to point out is that the reaction is in equilibrium. The second note I wanted to put down was that if the nucleophile is also a good leaving group, then the equilibrium favors the product side. Or, sorry, favors the starting material side. And then the opposite is true. If the nucleophile is a bad leaving group, then the equilibrium favors products. The last note is that aldehydes tend to be more reactive and favor products. So those are the main notes that you have to focus on whenever you're looking at nucleophilic addition to aldehydes and ketones. Is aldehydes tend to be more reactive, and then you also have to identify whether or not your nucleophile is also a good leaving group. Oftentimes we try to choose nucleophiles that aren't the best leaving groups if we are trying to favor formation of a product. All right, let's make a little bit of a chart here. I want to focus on different types of nucleophiles. So let's make a list of commonly used nucleophiles. And I'm going to break them apart by atom type. So I'll do oxygen, I'll do sulfur, I'll do nitrogen, I'll do hydrogen, and last but not least, I'll do carbon. Let's try to make a fairly exhaustive list here. All right, so oxygen nucleophiles. What are some nucleophiles that we could use? Hydroxide or water in this case, right? So we could have HOH, we could have hydroxide. What's another thing we could use? Yeah, we could do an alkoxide or an alcohol. The other one that we're going to see pretty commonly here is a diol. Diols are very commonly used as oxygen-based nucleophiles. And what's this diol called? You could call it 1,2-ethane diol, or more commonly, ethylene glycol. This is very commonly used as an oxygen-based nucleophile. So we'll see this a little later on in the chapter. Sulfur nucleophiles, pretty similar. You could use a super stinky gas or a super stinky liquid. Sulfur chemistry is very unpleasant, but sulfur is a really good nucleophile. The sulfur analog to the diol is often used in a very unique sort of reaction, and so we'll cover the reactivity of that a little later. For nitrogen, we know that we can have primary or secondary amines. They're pretty common. So I'll put in lone pairs here. Do you think tertiary amines are used very often? Yeah, not usually, just because they're so sterically bulked up that they have a really hard time attacking. So you usually see primary nitrogen nucleophiles. Occasionally you'll see secondary nitrogens acting as nucleophiles. All right, now we get into the tricky ones. How the heck can we treat hydrogen as a nucleophile? Let's think about it this way. Hydrogen that's H plus isn't a nucleophile, right? That's an electrophile. So we need H minus. So sodium hydride's a good idea. You do need hydride. However, sodium hydride, we said, doesn't dissolve very well. It's primarily used for acid-base chemistry. What's another source of hydride? Yeah, borohydride. So NaBH4 is a super common one. What's the other one? If we really want to amp it up? LAH. So lithium aluminum hydride is a really nice source of H minus. So we can use both of these. All right, and then for carbon nucleophiles, how can we turn carbon into a good nucleophile? Grignards. Heard somebody say that. RMGX. That makes carbon into a good nucleophile. Does anybody have an idea for another one? We saw it a little bit first term. I'll give you a hint. It smells like almonds and will kill you if it's protonated. Cyanide. So these are pretty common as nucleophiles, but like I said, try to keep it under relatively basic conditions, or else you may kill yourself. The last one that we haven't seen yet looks like this, where the carbon has a lone pair and a formal negative, and then we've got phosphorus, typically with 3 phenyl groups coming off of this. Yeah, it is. This is called an ylide, and we'll cover this when we get into the Wittig reaction but it's a really nice way of forming carbon-carbon double bonds. Does that make sense? Yep.
Does the sulfur also do other ones like oxygen as well?
Yeah, they're all pretty similar. Yeah, so this is a pretty good list, but there are obviously deviations from this. Before we head out, one thing I wanted to do is to give you guys a little bit of a hint on the pod because it's a little bit different. So if we look at pod 5's our first foray into biochemistry. Glucose, if we think about glucose, oftentimes it's drawn like the closed ring forms on the right, where you've got the cyclic glucose molecule. That's how they showed in most biology textbooks, right? However, glucose actually interconverts between the open chain and closed chain form. And if we look at the open chain form, glucose is actually an aldehyde in the open chain form. So what I want you guys to do is to show the nucleophilic attack and the ring closing mechanism for the open chain form of glucose going to the closed chain form. And in particular, this is under acidic conditions. This can also occur under basic conditions. I know this can be a little bit steppy, but make sure you keep track of carbons and that you try to make it somewhat clear. If you guys have any questions on the pod, I'd be more than happy to help, but I really want you guys to try to work your way through this whole mechanism, even though there's a lot of stuff hanging off of the glucose. All right, I'll see you guys tomorrow. I think we'll cut class off a little early today.